So next I am going to discuss the solutions for the questions numbering from 61 to 70 or so in the assignment in work per RG. In case you are not having any doubts in these questions from 61 to 72 or so, you can skip this class. So I am going to discuss the solutions here one by one, starting from 61. Again, look at the question number 61, which I have shown you in the previous class. A bullet is fired normally on an immovable wooden plank. It loses 25% of its kinetic energy in penetrating a thickness x of the plank. What is the total thickness penetrated by the bullet? So here we have to assume that retarding force on the bullet is constant. So let A denote the initial position of the bullet at which it begins to move inside the plank, which enters into the plank with kinetic energy K. Let B be the position of the bullet after it has penetrated thickness x of the plank. Let C be the final position of the bullet at which kinetic energy of the bullet becomes zero or bullet comes to rest. It is given that the kinetic energy of the bullet decreases by 25%. That is, the bullet loses 25% of its initial kinetic energy as it moves from the position A to the position B. Therefore, the remaining kinetic energy of the bullet at the position B will be 100% minus initial kinetic energy minus loss in kinetic energy, 25% of initial kinetic energy. That means the kinetic energy at B will be 75% of the initial kinetic energy at A, or 3/4 of the initial kinetic energy at A. So we'll solve this problem by the work energy theorem. According to the work energy theorem, change in the kinetic energy is equal to work done with external force on the bullet. Change in the kinetic energy means you can write final kinetic energy minus initial kinetic energy. That can be written as equal to work done with retarding force on the bullet. So for motion from A to B, A is the initial position, B is the final position. So initial kinetic energy at A, you can take K. Final kinetic energy at B is equal to 3K/4. I'm using this equation. This equation here. Final kinetic energy at B is 3K/4 minus initial kinetic energy at A is K, work done with retarding force. If F is the magnitude of the retarding force on the bullet, work done with retarding force will be negative, because the retarding force acts opposite to the displacement of the bullet. We can write minus F into X. So you simplify this, you get K/4 equal to F into X. Next, again we use the same equation for motion from A to C, because you are asked to find the total distance penetrated inside the plank. So for motion from A to C, you can take A as the initial position, C as the final position. So again we use the same equation, final kinetic energy at C minus initial kinetic energy at A is equal to work done with retarding force for displacement from A to C. Final kinetic energy at C is 0. Initial kinetic energy at A is K. Work done by the retarding force will be minus F into D. Or you can write K equal to F into D. So from first and second equations, You can substitute the value of K from second equation into the first equation. You get F into D by 4 equal to F into X. So you get the answer as 4X. So for question number 61, second option is the answer. See the question number 62. Bullet is fired normally on an immovable wooden plank. It loses 25% of its momentum in penetrating a thickness of 3.5 centimeter. The total thickness penetrated by the bullet. It also looks similar to the previous problem. The only difference is you have to momentum is given in terms of kinetic energy. So you have to express kinetic energy in terms of momentum and follow the method of the previous problem. The kinetic energy of a body in pure translatory motion, you can write P square by 2m. Where m is the mass of the body, P is the magnitude of linear to the body. So ratio the final kinetic energy to the initial kinetic energy. You can write P2 square by 2m divided by P1 square by 2m. K1 is the initial kinetic energy of the body of mass m, and K2 is the final kinetic of the bullet. You can write initial kinetic K1 equal P1 square by 2m. P1 is the magnitude of initial momentum. P2 is the magnitude of final momentum. So ratio the final kinetic energy to the initial kinetic energy equal square of the ratio of the magnitude of the final momentum and initial momentum. It is given that the bullet loses 25% of its momentum in penetrating a thickness of 3.5 centimeters. Let us suppose the bullet penetrates from A to B inside the plank in the first 3.5 centimeter distance. Next, C be the position of the bullet where its velocity becomes 0 and kinetic energy becomes 0. Let D be the total thickness penetrated inside the plank. So kinetic energy at A is P1, K1. Kinetic energy at B is K2. P1 is the momentum at A, P2 is the momentum at B. Momentum, 25% of momentum is lost. So final momentum will be 75% of initial momentum. So when 25% of initial momentum is lost in passing from A to B, the remaining momentum will be 75% of initial momentum. So P2 can write 75 by 100 times P1. So K2 will be equal to 9 by 16 times K1. Again, following the same procedure as we have done in the previous problem. Work energy from change in the kinetic energy equal to work done. For motion from A to B, change in kinetic energy equal to K2 minus K1 equal to work done by retarding force. Retarding force acts opposite displacement. Therefore, work done by retarding force is negative. That F into 3.5 centimeters. So here K2 is 9 by 10 times K1. So you get 7 by 16 times K1 equal to F into 3.5 centimeters. Next, we'll apply work energy theorem for motion from A to C. For motion from A to C, initial kinetic energy at A is K1, final kinetic energy at C is 0. So change in kinetic energy equal to final kinetic energy at C minus initial kinetic energy at A. That is 0 minus K1 is equal to minus F into D. Or you can write K1 equal to F into D. You substitute this value of K1 from second equation into the first equation. Substitute K1 from second equation into the first equation. So you get 7 by 16 into F into D equal to F into 3.5 centimeters. So you get D equal to 8 centimeters from here. That's the answer. If you want to copy the solution, you can take a pause and copy the solution. So for question number 62, first option is answer. See the question number 63. Body of mass m having momentum p is moving on a horizontal surface. If it stopped in a distance x, the coefficient of friction between the body and surface is given by. So in case you remember the conclusion I have discussed in one of the special cases in friction, you can do it directly in one step. That is stopping distance. If a body is given some initial speed u along a rough horizontal surface and left, then the distance traveled with the block before it stops during the retarded motion under the action of mg normally acts friction is given by u square s equal to u square by 2 nu g. U is the magnitude of initial velocity. That u can be written as p by m. In case you remember the conclusion which I have discussed in the past in friction in one of special cases under the heading stopping distance, you can directly answer in one step. Otherwise also you can answer, but you can apply work energy theorem. That is, I am discussing the alternate method, that is the method which you are supposed to follow for subject to type questions. Changing the kinetic energy is equal to work done by all the force acting on the body. The body is moving on the horizontal surface. Let us consider the force acting on the body. Its weight mg acts vertically downwards. Normal reaction force by the surface acts vertically upwards. Let small f denote the magnitude of friction force. It acts opposite to the direction of the motion. So change in the kinetic of the block is equal to total work done by all the forces. That is work done by the gravitational force plus work done by the normal reaction plus work done by the force of friction. Change in the kinetic energy equal to final kinetic energy minus initial kinetic energy. Final kinetic energy when it comes to rest is 0. The initial final kinetic energy minus initial kinetic energy. Work done by the gravitational force is 0 because the gravitational force mg acts perpendicular displacement. In this case, the displacement is in the horizontal direction. Gravitational force mg acts in the vertical direction. The same way work done when R reacts to 0. Work done with the force of friction, you can write minus Fk into S. So initial kinetic energy of the body is equal to Fk equal to nu k into normal reaction. Magnitude of normal reaction on the block can be written as mg here. And this initial kinetic energy you can write p square by 2m. So from this you get nu equal to S can be written as x here. So you get nu equal to p square by 2m square g into x. So first option is answer. See the question number 64 here. The kinetic energy acquired by mass m in traveling a distance starting from rest under acts of constant force. So you have to assume that the body moves on a smooth horizontal surface here, that F denotes the constant force applied on the body, which acts in the direction of the motion. The weight mg acts downward, normal reaction force acts upwards. According to the work energy theorem, the change in the kinetic energy of the body is equal to total work done by all the forces. Work done with a constant force F is equal to F into D. Work done with a gravitational force is 0 and work done with a normal reaction is 0. The change in the kinetic energy is equal to final kinetic energy minus initial kinetic. Initial kinetic is 0 if it starts from rest. That means final kinetic energy acquired by the body after it travels a distance d will be under acts of constant force will be F into D irrespective of the mass of the body. Therefore, second option is the answer, independent of m. Of course, velocity acquired depends on the mass m. Here v is the velocity acquired and kinetic energy acquired, you can write half mv square. In that case, v square will be 2f d by m. So that means the velocity acquired depends on the mass m, but kinetic energy acquired is independent of mass m for given values of f and d. See the question number 65 here. Particle of mass 0.1 kg subjected to a force which varies with distance as shown. If it starts its journey from rest at x equal to 0, its velocity at x equal to 12 meter is. So here also we'll apply the work energy theorem. To calculate the work done by the force, we have to calculate the area under the graph. Under the force displacement time graph, this force and not time, force displacement graph and displacement axis. The graph looks like in the form of a trapezium. So area of the trapezium, as you must be knowing, half into sum of the parallel sides multiplied by perpendicular distance between the parallel sides. So area of the trapezium is equal to half into sum of the parallel sides multiplied by perpendicular distance between the parallel sides. So here parallel length of one of the parallel sides, this length is equal to 8 minus, this length is 12 minus 0 or 12 meter plus length of this side. You can write same equal to 8 minus 4 meters into perpendicular distance between the two parallel sides. You can take 10 Newton. So this you can try to simplify further. So that will be 80 joules. So area under the graph and displacement as gives you work done. So applying work energy theorem, change in the kinetic energy of the body is equal to work done by the external force on the body. Change in the kinetic energy equal to final kinetic energy of the body minus initial kinetic. Final kinetic energy you can write half mv square. Initial kinetic is 0 because it starts from rest. Work done is given to be 80 joules. So now we can substitute mass m equal to 0.1 kg on the left hand side. And come on, copy down. If you those want to copy the solution, they can copy down the solution. So you get V equal to 40 meter per second. That's the answer. So for question number 65, fourth option is the answer. See the question number 66 here. Body of mass 5 kg rests on a rough horizontal surface of coefficient of friction point. The body is pulled to a distance of 10 meters by horizontal force of 25 Newton. The kinetic energy acquired by it is. Let us consider the forces acting on the body. Let F denote the magnitude constant. Magnitude the constant force applied on the body, which is given to be 25 newtons. Let Fk denote the magnitude of kinetic friction on the block during the motion, which acts opposite to the direction of the motion. The weight mg acts vertically downwards. The normal reaction force on the body by surface in contact acts vertically upwards. You can choose the horizontal direction of the x-axis and vertical upward direction of the y-axis. The y component of resultant force of the body denoted by Fy, which you can write n minus mg. But there is no acceleration parallel to y-axis, so this must be 0. Therefore, magnitude of the normal reaction of the body is the same as the magnitude of its weight mg. And magnitude of force of kinetic friction is equal to product of the coefficient of friction into magnitude of normal reaction. That we can write mu mg. According to the work energy theorem, change in the kinetic energy of the body is equal to total work done by all the forces. That is work done by the constant force F applied plus work done by the frictional force plus work done by the gravitational force plus work done by the normal reaction. Change in the kinetic energy is equal to final kinetic energy minus initial kinetic energy. Final kinetic energy is required. You have to find. The initial kinetic energy is 0 because it is initial at rest. Work done with a constant force applied on the body in the direction will be given by F into S because the force acts in the direction of the displacement. Work done with the force of friction, you can write minus Fk into S because force of kinetic friction acts opposite to the direction of displacement of the body. Work done with the gravitational force is 0 because the gravitational force acts perpendicular to displacement. In the same way, work done with the normal force is 0. Therefore, final kinetic energy of the body can write F minus Fk can be written as nu into mg into S. Here F is given to 25 newtons. Nu is given to 0.2, mass of the body is 5 kg, G is 10 meter per second square. And mass of displacement is 10 meters. So you get the answer as 150 joules. So for question number 66, second option is the answer. See the question number 67. The body is moving up an inclined plane of angle theta with initial kinetic energy E. The coefficient of friction between the plane and the body is nu. The work done against friction before the body comes to rest is. So to calculate the work done against friction before the body comes to rest, you have to know the distance which the body travels along the inclined plane before it comes to rest. So here you can solve the problem by the dynamics method. As I discussed in the past, in the friction chapter, Newton's laws of friction, the block is projected up along a fixed inclined plane with initial speed u and left. Then the acceleration of the block during ascent when it moves with retardation under the action of forces, narrow reaction mg and kinetic friction is given by A equal to minus g into sine theta plus nu cos theta. Nu is a question of sliding friction here between the body and inclined surface. To find the distance the body travels before it comes to rest, can use the equation v square on square equal to s. If the coefficient of friction between the body and the surface is constant, then acceleration can be assumed to be constant. When it comes to rest at the highest possible position up to which it moves, final velocity is 0. Let us the distance it travels of the inclined plane before it stops. Can take A equal to minus g into sine theta plus nu cos theta. So distance the body travels up along the inclined surface before it stops, before its velocity momentarily becomes 0, u square by 2g into sine theta plus nu into cos theta. So work done against friction means it is negative of work done by the friction force. So work done by the friction force of the body we write minus Fs, because force of friction acts opposite to the direction of displacement. Magnitude of friction force acting on the body when it is moving up the inclined plane, you can write nu into magnitude of normal reaction. Magnitude of normal reaction in this case you can write as mg cos theta. And S can be written as u square y from here 2g into sine theta plus nu cos theta. So work done, this you can write half mu square can be written as equal to the initial kinetic energy denoted by E. So you can substitute half mu square equal to E. Therefore minus nu E cos theta by sine theta plus nu cos theta. That is work done by friction force on the body. So work done against friction will be negative of work done by the friction force. So you get nu E cos theta by sine theta plus nu cos theta. If you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So for question number 67, fourth option is the answer. See the question number 68. Stone of mass m is thrown from Earth's surface at an angle alpha to the horizontal with an initial velocity v0. Ignoring the air drag, the power developed by the gravity force t seconds after the beginning of the motion. So let us choose the horizontal direction parallel to the horizontal velocity of the stone as positive direction of x-axis and vertically upward direction as positive direction of y-axis. So the only force acting on the projectile is weight or gravitational force, that you can write mg bar. The gravitational force acts vertically downwards in the negative direction of y-axis. So j cap is unit vector along positive direction of y-axis. So gravitational force acts vertically down negative direction of y-axis. So minus j cap is a unit vector in the negative direction of y-axis. A vector can be written as product of its magnitude and unit vector in the same direction. So we have written F bar as here minus mg into j cap. The velocity v bar at any instant you can write Vx into I cap plus Vy into j cap. Vx is x component of the velocity, which you can write V naught into cos alpha. Vy is the y component of the velocity of the projectile, which you can write Uy plus Ay into t. Uy is the initial velocity in the vertical direction. That is equal to V naught into sin alpha. Here initial velocity has magnitude V naught, that makes an angle alpha to the horizontal. Acceleration in the y direction is equal to minus g. This equations are written based on theory of projectile motion. So power developed by the force of gravity after time t, I mean instantaneous power, can write F bar dot V bar. So dot product of two vectors you can write as product of the x components plus product of the y components for two vectors in the xy plane. Here x component of the force is 0 because the force has no component along x-axis. It has only force acts in the y direction. Fy you can write minus mg. And Vy you can write V naught sin alpha minus gt. So you get this as mg into gt minus V naught into sin alpha. That will be the answer. So for question number 68, first option is the answer. See the question number 69. Block of mass 10 kg is moving in x direction with a constant speed of 10 meters per second. It is subjected to retarding force F equal to 0.1x joule per meter during its travel from x equal 20 meter to x equal 30 meter. Its kinetic energy will be. Here F represents the magnet of the retarding force which acts opposite to the displacement of the block. Here displacement of the block is along x-axis. So we have to assume that the block moves against the retarding force on a horizontal surface. So that we can assume that no work is done by the gravitational force. So now work done with retarding force cannot be simply written as minus Fs as we have written in the previous examples, because here retarding force is not constant, it is varying with the displacement. So it is a variable displacement. So work done by variable force has to be calculated by the method of integration. So work done with retarding force for infinitesimally small displacement, you can write minus F into dx, because the retarding force acts opposite displacement. That is minus 0.1 into x dx. So total work done with retarding force when the body moves from x equal to 20 meters to x equal to 30 meters can be found by integrating this dw from x equal to 20 meter to 30 meter. So that will be so it is a simple integration. Integral of x power n dx, you can add x power n plus 1 by n plus 1. Using that formula, that is minus 0.1 into 0.1 joule per meter into x square by 2, 20 meter to 30 meter. Now we'll apply the limits here. So find the value of function for upper limit minus value of function for lower limit. So the work done with the retarding force you get minus 25 joules. According to the work energy theorem, change in the kinetic energy of the body is equal to work done by the external force on the body. Change in the kinetic energy is equal to final kinetic energy minus initial kinetic energy. That is equal to work done. The initial kinetic energy of the body is equal to half into mass of the body into square of the initial speed of the body. The mass of the body is 10 kg here. The initial speed of the body is 10 meters per second. So if you calculate the initial kinetic energy of the body, that comes out to 500 joules. The work done by the retarding force is minus 25 joules. So you can solve for final kinetic energy here. So you get final kinetic energy of the body will be equal to 475 joules. This is the answer. So for question number 69, first option is the answer. See the question number 70. Particle of mass 20 gram is thrown vertically upwards with a speed of 10 meters per second. The work done by the force of gravity during the time the particle goes up is. You can solve the problem two methods. One method is by applying work energy theorem. So the particle is projected vertically upwards with an initial speed u equal to 10 meters per second. Let A be the point of projection of the particle. Let B be the highest point up to which the particle moves, where its velocity becomes 0. So change in the kinetic of the particle is equal to work done with the external force of the particle. Only force is equal to work done with gravitational force. Change in kinetic energy is equal to final kinetic at the highest position minus initial kinetic energy at the point of projection. So work done with the gravitational force of the particle when the particle moves reaches the highest position during the time of ascent, when it moves upwards minus half mu square. M is equal to 20 grams means 20 in 10 power minus 3 kg in a size system. Initial speed of projection is 10 meters per second. So you get minus 1 joule is the answer. You can also do the problem by other way. The maximum height reached by the particle when it is projected vertically upward with initial speed u from theory of kinematics. For motion under gravity, u square by 2g. Here initial speed is u equal to 10 meters per second. If you take g as by g, or first you write this way, then work done with the gravitational force when the body rises to a vertical height h will be minus mgh. I mean, this is alternate method. H equal to u square by 2g, or again minus half mu square. That means you get the same answer after substitution and simplification. So for question number 70, first option is the answer. See the question number 71. A force exerts an impulse J on an object of mass m, changing its speed from v1 to v2 along a smooth horizontal floor. The force and the object's motion are along the same straight line. The work done by the force is. Now the impulse J you can write change in the momentum, because The problem is given with one-dimensional motion. That means all the impulse, initial velocity, final velocity, and force and displacement all are in the same direction. Therefore, magnitude of the impulse is equal to difference in the magnitude of final and initial momentum here, because V bar, V1 bar, V2 bar, and J bar all are in the same direction here. So work done I denoted by W. Work done by the force equal change in the kinetic energy. From work energy theorem. When the body is moving on smooth floor, no work is done by the gravitational force and no work is done by the normal reaction force by the floor. So work done by the force applied on the body in the direction of its motion can be equated to the change in the kinetic of the body. So W can be varied by J. Change in the kinetic energy equal to final kinetic energy minus initial kinetic energy. That is half mv2 square minus half mv1 square. Can divide W with J. That is half m into v2 square minus v1 square. You can write v2 minus v1 into v2 plus v1. J can be written as m into v2 minus v1. So m into v2 minus v1 get cancelled. So you get W equal to J into v1 plus v2 y2. That's the answer. So for the question number 71, third option is the answer. See the question number 72. A 1000 kg block of granite is dragged up an incline at a constant speed of 1 meter per second by a steam winch. The question of kinetic friction between the block and the incline is 0.4. How much power must be supplied by the winch? So we have to calculate the work done by the force developed by the winch. Let F denote the force applied on the block parallel to the inclined surface with the help of the winch. Let capital F be the magnitude of force acting on the block parallel to the inclined surface developed by the winch, which tends to move it up the inclined plane. To calculate the power, you have to calculate the magnitude of the force applied by the winch. That is one method. Other method is you can apply work energy theorem to calculate work done by this force F. Because you are not given the time interval T here, we'll try to find the magnitude of force applied by the winch here. So here, let theta denote the angle of inclination of the inclined path to the horizontal. So magnitude of the displacement or length of the inclined path will be equal to under root of 30 square plus 40 square in meters. Or 50 meter. So sine theta from the figure you can write height of the inclined plane divided by length of the inclined plane. So 30 meter by 50 meter or 3 by 5. You get cos theta from that equal to 4 by 5. So if you consider the forces which act on the block here, the weight mg of the block acts vertically downwards. The narrow reaction force acts perpendicular to the inclined surface and directed away from the inclined surface. The force of kinetic friction acts down the inclined path. You can resolve the weight mg into components parallel to the inclined surface and perpendicular to the inclined surface. The component mg sin theta acts parallel to the inclined surface and the component mg cos theta acts perpendicular to the inclined surface. You can choose the direction of the motion of the block as x-axis. The matter of force of kinetic friction, you can write nu k into n or nu k into mg cos theta. Resultant force of the block along x-axis equal to capital F minus mg sin theta minus fk. So Newton's second law, that is equal to mass into acceleration. But here it is moving with constant velocity. So acceleration is 0. Therefore, magnitude of the force acting on the block parallel to the inclined surface developed by the winch is equal to mg sin theta plus fk. Can substitute fk equal to uk into mg cos theta. This you get mg into sin theta plus nu into cos theta or nu k into cos theta. The mass is m is given to be 1000 kg. G is given to be 10 meter per second square. Sin theta I can take 3 by 5. Nu is 0.4 and cos theta equal to 4 by 5. This will be Newton. Can solve for this. So the power delivered by the winch is equal to F into V, because force developed by the winch acts in the direction of the velocity. You can complete the simplification part. So you get 9.10 cube newtons. So power is equal to